Detroit, 1958. Sputnik circled overhead, and every American kid knew the future ran on atoms. Uranium wristwatches, plutonium kitchens, nuclear-powered everything. When Ford wheeled out a sleek, salmon and white concept car with a miniature reactor where the trunk should be, nobody laughed. They leaned closer. The Nucleon wasn't a joke. It was a 3/8 scale model representing thousands of engineering hours, and Ford's genuine belief that by 1963 you'd swap depleted uranium cores at service stations and drive 5,000 miles without burning gasoline. The thing looked like a jet fighter mated with a Jetsons cartoon. Fins swept back like stabilizers, passenger cabin pushed forward, and a bulbous nacelle housing a compact nuclear steam engine in back. It debuted at the Chicago Auto Show in January 1958, parked among fever dream concept cars. But while others sold chrome and V8 machismo, the Nucleon sold the future itself, an era when petroleum would be obsolete, when nuclear energy would be so cheap that range anxiety would vanish. Visitors crowded around it like a moonlander, because it was the vehicle that would carry America into the atomic tomorrow. The Nucleon didn't emerge from a vacuum. It came out of a specific moment in American industrial history when the lines between science, salesmanship, and sheer goddamn hubris were blurrier than they'd ever been. The guy who greenlit the project was a Ford executive named Manny, short for Emmanuel, a vice president in the styling division who'd made his name pushing the Edsel. Yeah, that Edsel. The car that became a punchline. But in 1956, when the Nucleon was taking shape on the drafting tables, the Edsel was still a coming attraction, and Manny was riding high on the belief that American consumers wanted spectacle, innovation, and a future that looked like it had been designed by Buckminster Fuller. The actual design work fell to a team led by Jim Powers, an industrial designer who'd spent the early 50s working on everything from kitchen appliances to missile nose cones for Convair. Powers understood aerodynamics, materials science, and the theatrical power of a clean reveal. His sketches for the Nucleon emphasized lightness, efficiency, and visual drama. The reactor housing wasn't hidden, it was celebrated, shaped like a streamlined torpedo and positioned so it dominated the car's rear profile. This wasn't apologetic design. This was a middle finger to the internal combustion engine, rendered in fiberglass and optimism. But the real brains behind the concept, at least the engineering fantasy, came from outside Ford entirely. The Atomic Energy Commission had been running feasibility studies on portable reactors since 1954, and one of their white papers landed on a desk at Ford's research division in Dearborn. The document was pure speculative engineering. If you could miniaturize a pressurized water reactor down to the size of a deep freezer, and if you could shield it adequately, and if you could design a heat exchanger that wouldn't crack under thermal cycling, then theoretically, you could generate enough steam to drive a turbine that would power an electric motor that would turn the wheels of a car. The chain of ifs was longer than a freight train, but Ford's engineers didn't see obstacles. They saw a design challenge, so they sketched it out. A compact reactor core, uranium-235 maybe, or thorium if the metallurgy worked out, encased in a lead-and-boron shield weighing somewhere between 800 and 1,200 pounds. That shielding was the killer. You couldn't skimp on it because even a low-power reactor pumps out gamma rays and neutrons that'll cook you from the inside out. But you also couldn't make the car weigh 6,000 pounds, because then the whole fuel efficiency argument collapsed. Ford's proposed solution was layered shielding. Dense materials close to the core, lighter composites farther out, and a cooling system that circulated water through channels in the shield itself to prevent thermal warping. None of this had been built. None of it had been tested. But on paper, it worked. And in 1956, working on paper was enough. Here's how the Nucleon was supposed to work, according to Ford's promotional materials and the breathless coverage in Popular Mechanics. You'd start the car by engaging the reactor control rods, which would begin the fission chain reaction inside the core. As uranium atoms split, they'd release heat, lots of it, concentrated in a small space. That heat would boil water in a closed-loop primary system, creating high-pressure steam. The steam would drive a compact turbine, which would spin a generator, which would produce electricity to power electric motors mounted on the rear axle. The whole thing was envisioned as a hybrid of submarine propulsion and automotive engineering. Naval reactor tech shrunk down and stuffed into a passenger car. The control rods were the crucial piece. In a traditional reactor, you lower rods made of neutron-absorbing material, boron, cadmium, hafnium, into the core to slow or stop the reaction. Raise them, and the reaction accelerates. Heat up, cool down, throttle response. It was all supposed to be managed by a driver interface that looked, in Ford's concept sketches, like a combination of a fighter jet's throttle and a home thermostat. You wouldn't have a gas pedal in the traditional sense. You'd have a power demand lever. Push it forward, and the reactor control system would automatically adjust the rods to increase steam output. Ease off, and the reaction would dampen, coasting on residual heat. Range was the big selling point. Ford claimed the Nucleon could go 5,000 miles on a single fuel load, an absurd number in 1958, when the average American car got maybe 15 miles per gallon and a full tank lasted 300 miles. The math was fuzzy, but the logic was sound. Nuclear fuel has energy density that makes gasoline look like firewood. A few pounds of enriched uranium contains the thermal equivalent of thousands of gallons of gas. If you could tap even a fraction of that energy efficiently, you'd have a vehicle that could drive cross-country without refueling. No gas stations, no oil companies, just a nationwide network of atomic service centers where technicians in lead aprons would swap out your depleted core for a fresh one using remote manipulators and Geiger counters. Of course, there were complications. The first was shielding. Even with 1,000 pounds of lead and boron wrapped around the reactor, you'd still be sitting 10 feet away from an active fission reaction. Gamma radiation doesn't give a shit about fiberglass body panels or upholstered seats. It goes through them like they're not there. Ford's engineers assumed, hoped, really, that you could design the shielding so that radiation exposure in the passenger cabin stayed below background levels, but nobody had actually built a prototype to test that assumption. The model on the show floor was non-functional. It was a sculpture of a dream. The second complication was crashes. Imagine a freeway pileup involving a nuclear-powered sedan. The reactor core wouldn't explode. Fission bombs and reactors work on completely different principles. But you'd have shattered shielding, ruptured cooling systems, and possibly molten fuel scattering across the roadway. Cleanup wouldn't involve tow trucks and brooms. It would involve hazmat teams, evacuations, and a Superfund site where the intersection used to be. Ford's publicity materials didn't mention this. They showed happy families cruising through Monument Valley, mountains in the background, reactor humming quietly in back, nobody wearing dosimeter badges or lead-lined underwear. To understand why Ford thought this was remotely plausible, you have to understand the cultural moment. 1958 was peak atomic age optimism. The United States had just launched its first nuclear submarine, the USS Nautilus, which had sailed under the North Pole on reactor power. The shipping port reactor in Pennsylvania was feeding electricity into the commercial grid. General Electric and Westinghouse were pitching nuclear plants to utilities as the energy source that would make coal and oil obsolete. And the public, Jesus, the public ate it up. kids played with chemistry sets that contained actual radioactive samples. Families visited Atomic Energy Commission exhibits at state fairs where smiling technicians demonstrated miniature reactors and explained how atoms could cure cancer, desalinate oceans, and power spaceships to Mars. Detroit was fully on board. Ford wasn't the only automaker chasing atomic dreams. In 1953, Studebaker had commissioned a designer named Lauren to sketch an astral concept car powered by a radioactive capsule, though the details were even vaguer than Ford's. In 1962, Chrysler would roll out the turbine car, which wasn't nuclear, but used a similar heat exchange principle. Burn anything that combusts, including Chanel No. 5, as one promotional stunt demonstrated, and use the heat to spin a turbine. The logic was the same. If you could decouple propulsion from petroleum, you'd have a car that could run on the fuel of the future, whatever that turned out to be. Ford's confidence wasn't entirely delusional. The company had invested heavily in jet engine research during World War II and had relationships with the Atomic Energy Commission through military contracts. They knew people at Los Alamos, at Oak Ridge, at Knowles Atomic Power Laboratory. When Ford's engineers claimed they could build a compact reactor, they weren't talking out of their asses. They were extrapolating from real technology, submarine reactors, aircraft reactor experiments, the crazy aircraft nuclear propulsion program that ran from 1946 to 1961, and assuming that if you could make a reactor small enough to fly, you could make one small enough to drive. What they underestimated was the engineering gap between theoretically possible and actually buildable. Submarine reactors worked because submarines are big, heavily shielded, and operated by trained crews. Aircraft reactors never worked. The program burned through $1 billion and produced exactly 0 functional planes before being canceled. And car reactors? Car reactors faced all the challenges of aircraft reactors, plus the additional nightmare of making them civilian-safe, crash-resistant, and affordable enough to sell at a dealership. Ford knew this. They just chose to believe that the problems were solvable, because the alternative, that the internal combustion engine would remain dominant for decades, was too boring to contemplate. The Nucleon made its public debut at the Chicago Auto Show on January 18, 1958, and the reaction was split down the middle. The automotive press loved it. Motor Trend ran a feature titled Ford's Atomic Dream Machine, complete with cutaway illustrations showing the reactor, turbine, and drivetrain. Popular Science did a spread on Cars of Tomorrow with the Nucleon front and center. The tone was reverent, almost worshipful. Here was American ingenuity at its finest, a car that represented everything the space age promised. But outside the enthusiast bubble, people were less thrilled. The scientific community, particularly nuclear physicists who actually understood reactors, looked at Ford's claims and started asking uncomfortable questions. How would you refuel the damn thing? Where would the spent fuel go? What happens when some drunk teenager rear-ends a Nucleon at 70 miles per hour and cracks the reactor vessel? Ford's promotional materials glossed over these details, offering vague assurances about service centers and trained technicians. But anyone who'd worked with radioactive materials knew the reality would be a regulatory and logistical nightmare. The Atomic Energy Commission, which had initially been supportive of portable reactor research, started distancing itself from automotive applications almost immediately. Internal memos from 1958 show AEC scientists expressing alarm at the public perception that nuclear cars were just around the corner. One memo, declassified in the 1990s, warned that premature commercialization of reactor technology in consumer products could undermine public confidence in nuclear power generally. Translation: If a nuclear car melts down in someone's driveway, it's going to make building civilian power plants a hell of a lot harder. Insurance companies were even less enthusiastic. Underwriters looked at the Nucleon concept and saw an uninsurable catastrophe waiting to happen. Who'd be liable if a reactor leak contaminated a neighborhood? Ford? The driver? The uranium supplier? The regulatory framework didn't exist. Nobody had written policies for nuclear-powered consumer vehicles because nobody had imagined anyone would be stupid enough to try building them. Ford's legal team quietly shelved any plans to move beyond the concept stage, and the Nucleon remained what it had always been, a 3/8 scale model, a beautiful lie, a sculpture of a future that would never arrive. Even if the regulatory and safety problems had somehow been solved, and they couldn't have been, the Nucleon faced a more fundamental obstacle. The physics just didn't work. Not in 1958, not with the materials and engineering tools available at the time, and arguably not ever. The core problem was power-to-weight ratio. A nuclear reactor generates heat continuously. You can't turn it off like a light switch. Even with control rods fully inserted, the reactor still produces decay heat from fission byproducts. That means you need a cooling system running 24/7, whether the car is moving or parked. Submarine reactors handle this with massive seawater heat exchangers. The Nucleon would have needed a radiator the size of a barn door, or an active cooling system with electric pumps, which would drain power and add weight, which would require a bigger reactor, which would add more weight, in a vicious cycle that made the whole concept collapse under its own mass. Then there's throttle response. Internal combustion engines react instantly to driver input. Push the gas pedal, fuel, and air mix, combustion happens, power increases, all within milliseconds. A nuclear reactor can't do that. Raising and lowering control rods is a slow process, governed by thermal inertia and neutron flux dynamics. Even the fastest naval reactors take seconds to minutes to ramp power up or down. Imagine trying to merge onto a freeway with a propulsion system that takes 30 seconds to spool up, or trying to brake, except your heat source can't shut off. So regenerative systems have to absorb and dissipate megawatts of thermal energy. The engineering required to make that work would have been staggering. And then the real killer, there was fuel enrichment and supply. The Nucleon's reactor would have required enriched uranium, the same stuff used in weapons and submarine reactors. In 1958, the entire U.S. enrichment capacity was dedicated to military applications and early civilian power reactors. The idea that you could divert enough enriched uranium to power consumer vehicles was fantasy. Even if production scaled up massively, the cost would have been prohibitive. Gasoline was cheap. Uranium enrichment was the most expensive industrial process ever invented. No middle-class family was going to pay $50,000 for a car when a Chevy Bel Air cost $2,500. By 1960, Ford had quietly stopped mentioning the Nucleon in press materials. The model was packed away in storage, wheeled out occasionally for vintage car shows and retro-futurism exhibits. Engineers who'd worked on the project moved on to other concepts: turbine cars, fuel cells, eventually hybrids and electrics. The dream of a nuclear sedan faded into the same cultural graveyard as flying cars and jetpacks, another atomic promise that reality couldn't cash. But here's the thing about the Nucleon. It never entirely died. It became a totem, a symbol of the atomic age's wild ambitions and catastrophic blind spots. Today, the original 3/8 scale model sits in the Henry Ford Museum in Dearborn, Michigan, displayed alongside the Lincoln Continental Kennedy was shot in, and the Rosa Parks bus. It's positioned in a section titled Driving America, surrounded by vehicles that actually existed, actually drove, actually shaped history. And there, among them, is the Nucleon, a car that never turned a wheel, never burned a milligram of uranium, never came within 1,000 miles of production, but which represents something maybe more important than any of the real cars around it. The moment when America believed technology could solve any problem, when the future looked like a streamlined wonderland, when atoms were magic and engineers were wizards. The Nucleon shows up constantly in retrofuturism, in alternate history fiction, in video games set in bombed-out wastelands where nuclear cars would have been the norm. It's in the Fallout games, in steampunk car shows, in concept art for dystopian futures. It's become shorthand for the future we didn't get, the road not taken, the timeline where we went all in on atoms instead of oil and either solved all our problems or irradiated ourselves into extinction. Probably both. Serious nuclear historians look at the Nucleon as a cautionary tale, evidence of how detached the atomic age's promises were from physical reality. But car enthusiasts see it differently. They see a design triumph, a vehicle so beautiful and strange that it transcends its own impossibility. The proportions are perfect. That pushed forward cabin, the long rear deck, the fins that aren't tacky because they're structural, meant to stabilize the car at the high speeds a nuclear reactor could theoretically sustain. It looks fast, standing still. It looks like it belongs in a future that's cleaner and bolder and more hopeful than the one we got. And maybe that's the real legacy. Not that Ford tried to build a nuclear car, plenty of companies chased dead-end technologies, but that they built a dream so beautiful, so precisely rendered, that people still want to believe in it 70 years later. The Nucleon didn't fail because it was a bad idea. It failed because reality is harder than dreams. Because physics doesn't care about your press releases, because you can't engineer around fundamental constraints no matter how talented your designers are. But the dream itself, the idea that we could power our lives with star stuff, that we could break free from fossil fuels and scarcity, and the geopolitical nightmare of oil dependence, that dream was real. The Nucleon was just the wrong vessel for it. The story doesn't end in 1960, because even after Ford abandoned the Nucleon, even after the Atomic Energy Commission shut down automotive reactor research, people kept trying. Not at Ford, they'd learned their lesson, but in backyard workshops, in university labs, in fringe engineering circles that refused to accept that nuclear cars were impossible. In 1965, a team at the University of Michigan built a working model of a thorium-powered vehicle. Not a car, exactly, but a motorized platform that could move under its own nuclear power for about 15 feet before the shielding overheated and they had to shut it down. The experiment was classified for decades, buried in Cold War secrecy, and only came to light in a 2003 dissertation that nobody read. In 1978, a metallurgist named Wallace from Ohio, no relation to the drag racer, filed a patent for a compact fission heat source for vehicular applications. His design used a tiny solid-core reactor, no bigger than a toaster, cooled by liquid sodium and shielded with borated polyethylene. The patent was granted in 1981. Wallace built a prototype in his garage, tested it on a dyno, got heat output numbers that looked promising, and then the Nuclear Regulatory Commission showed up and told him to dismantle it immediately or face federal charges. He complied. The prototype was buried in a hazardous waste facility outside Cincinnati. As late as 2009, engineers at Laser Power Systems were pitching a concept for a thorium-powered car that used laser ignition instead of control rods, a more responsive, theoretically safer system. They claimed they could build a working prototype for $2 million, nobody funded it. By then, Tesla had proven that battery electric vehicles could be fast, practical, and sexy, and the appetite for nuclear propulsion had evaporated entirely. All of these attempts, the University of Michigan platform, Wallace's garage reactor, the Laser Power Systems pitch, trace their lineage back to the Nucleon, not in terms of actual engineering inheritance, but in terms of inspiration. They all started with someone looking at Ford's 1958 concept and thinking, what if we could actually make this work? They couldn't. Nobody could. But the trying mattered because it kept alive the idea that propulsion technology wasn't fixed, that the internal combustion engine wasn't the final answer, that somewhere out there was a better way to move. Today, if you want to see the Nucleon, you fly into Detroit, rent a car, gas or electric, never nuclear, and drive 20 minutes west to the Henry Ford Museum. You pay your admission, walk past the Wright Flyer and the Allegheny steam locomotive and Thomas Edison's Menlo Park lab, and eventually you reach the automotive wing. The Nucleon is there, under soft lights, behind velvet ropes, looking exactly as it did in 1958. The salmon and white paint is still perfect. The fins still sweep back like a fighter jet's. The reactor nacelle still dominates the rear profile, smooth and ominous and utterly unreal. There's a placard next to it, small and understated, explaining what the car was supposed to be. It doesn't mention the impossibility, the radiation risk, the engineering gaps. It just says, Ford Nucleon Concept Car, 1958. Proposed nuclear-powered vehicle. Never produced. And people walk by, and some of them stop, and they stare at it the same way visitors in 1958 stared at it, with a mix of awe and confusion, and the unsettling feeling that they're looking at something from a parallel universe. Because that's what the Nucleon is, a transmission from a future that never happened. Preserved in a museum of futures that did. It sits there next to the Model T and the Mustang and the Tesla Roadster, cars that changed the world. And it doesn't belong. But it absolutely belongs. Because it represents the path we almost took, the future we almost believed in, the dream we almost made real. And sometimes, late at night, when the museum is closed and the lights are off and the cars sit silent in the darkness, you can almost imagine the Nucleon humming softly, its reactor glowing in the shadows, waiting for a tomorrow that will never come.